Hi, so this is a little odd, but what I found is that showing a video over Zoom doesn't work very well. So what we're going to do is I'm recording the video while it's on my screen. I'm going to stop it and talk about certain parts that are important, right? Then after this is all done, we'll come back together in the Zoom and you can ask whatever questions you have. So make sure that you have some paper in front of you and that you're ready to ask questions, okay? So we'll see how this works for you.
Now, how are all these levels
So
actually?
already there's something to tell you. First of all, this is MIT, right? Massachusetts Institute of Technology. The first thing that you'll want to notice is all of the amazing chalkboards. I want to point that out because it's pretty cool.
Measured in a in these atoms. I mean, it's enough to have these nice, I'd say, beautiful chalkboard renderings of these levels and stuff, but it's also nice to measure them. And one of the ways, there's a number of different ways, but one of the ways that we talk about in 3091 is photoelectron spectroscopy. And the basic idea is the following. I take an atom beam, an atom beam like this. And I said that too fast. Electron spectroscopy. It's a lot like the photoelectric effect that we talked about before, except instead of a solid surface, this is with atoms. So I take my atom beam, and then from this side, I take typically an X-ray source, super high energy photons. So much energy that they have at least the energy sufficient to knock out inner shell electrons.
Okay, so first let's talk about the atom beam and that X-ray. So the atom beam for us would be an element, right? So they would take an element of atoms of the element and shoot it into this machine. And then the X-ray, as he was talking, it's a photon of really high energy. And it's such high energy, he's going to mention this, I'll rewind it a little bit, such high energy that it knocks the electrons off of the atom, okay? So let me just back it up just a little bit for you.
Photons. So much energy that they have at least the energy sufficient to knock out inner shell electrons from the atoms.
So the inner shell electrons, we're not talking about just the valence electrons, the electrons on the very outside. We're talking about, for photoelectron spectroscopy, we're talking about every single electron in that atom. Now they come out in shells, okay? So that's important to remember that they come out in shells.
And so I create this cloud of electrons that come out. And then what I do is outside this chamber here, I have a big magnetic field, which is going into the board. And since I have a charged particle now, magnetic field into the board, it experiences the Lorentz force we talked about, and so it gets bent. And if it's traveling with a high kinetic energy, it'll go like that. And if it has a low kinetic energy, it'll go like that. And what this does is it allows me to move a detector here along this and actually get a energy spectrum, the kinetic energy spectrum of these electrons.
Okay, so let me tell you what's going on so far. So we have this atom beam, which is an element. So let's just say an element, magnesium, right? And so we are shooting magnesium into this machine. Hitting those magnesium atoms is a very high photon beam. In this case, he's saying it's an X-ray. Okay, X-ray has lots and lots of energy. That X-ray is making all of the electrons, it's kicking all the electrons out of the atom. And it's doing that by supplying energy to the atom. Now, what happens is that the electrons, and this is what he's talking about right here, those electrons come out at different kinetic energies. So in other words, they come out at different velocities. Okay, what determines that velocity he'll talk about here in a second. But if it has really high energy, it comes way over here. If it has really low energy, it comes here. And then there's this detector that beep, 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 beep goes along this path, and then it detects those electrons. Okay, so let me back it up just a second and we'll get going again here.
Along this and actually get a energy spectrum, the kinetic energy spectrum of these electrons. Now, if we do a balance, we have the energy of the photon coming in.
Okay, the energy of the photon, he's talking about the X-ray, all right? So the photon that we're putting into this system is an X-ray photon. I'm going to back it up a little bit.
Of these electrons. Now, if we do an energy balance, we have the energy of the photon coming in.
That's the X-ray.
We have the kinetic energy of the electron that left. And that had better equal the binding energy of that electron. Or, sorry, the sum of the kinetic energy of the electron plus the binding energy, the energy required to remove it from the atom, had better equal the energy of the photon that we used to smack into the atom.
Okay, so Coulomb's law, right? We have, in the atom, what do we have? We have protons, and then we have electrons. That's the positive and the negative for Coulomb's law. So those electrons are being held with a certain force of attraction because of Coulomb's law. Now, as it turns out, that energy binding that he's talking about here, that is the force of attraction. That's the amount of energy that's needed to break the electron from the proton. Okay, that's the binding energy. So as it turns out, the kinetic energy, remember these electrons are coming out with a lot of energy, right? That's the kinetic energy. The energy of the photon, in this case the X-ray, the X-ray does not equal the kinetic energy. Why not? Well, because it takes energy to remove the electron from the atom. So that's why the energy of the photon does not equal the energy that the electron is coming out with, because it took energy to remove that electron. And what this photoelectron spectroscopy shows us is basically this binding energy. We can take the energy that we start out with, so from the X-ray, and we can subtract out the energy that the electrons are coming off with, so that kinetic energy. That leaves us with the binding energy, which is the amount of energy that is required to remove the electron from the atom. Why does it take energy to remove the electron from the atom? Because the protons are attracting the electrons. Okay, let's keep it going here. That's the whole point of photoelectron spectroscopy. That was my whole thunder right there. But let's go ahead and watch this anyway. I'm gonna rewind it a little bit more. That's good. All right.
We have the kinetic energy of the electron that left, and that had better equal the binding energy of that electron. Or, sorry, the sum of the kinetic energy of the electron plus the binding energy, the energy required to remove it from the atom, had better equal the energy of the photon that we used to smack into the atom. So this binding energy is what we want. This is the energy. If I go, this is the right one? Yeah. Let's use this one. Let's say I want to smack out this electron right here. I want to know how deep this is. Right? Up here is 0. I want to grab that electron and pull it out and measure how much energy it had down here. That's basically the energy of what it takes to move it. So the binding energy is basically that level, and it looks like. So I know this because that's the X-rays I used. I know this because I measured it with my detector. I know where the electron came out, so I know its kinetic energy. So let's just end with photoelectron spectrum. So this is the intensity, the number of photoelectrons per unit area per time. So this is called the photocurrent.
So he used the term intensity. Think of this the same way that we talked about mass specs, okay? So the isotopic abundance of isotopes that make up an element, that's the intensity. Think about it the same way.
And this is my binding energy, and it's traditional to write increasing energy from right to left.
Okay, so increasing energy from right to left, that means over here, this is going to be 0, and then over here, this is going to be high. Okay, so this is big numbers, little numbers.
And if this were nitrogen, remember that's 1s2, 2s2, 2p3, I'd get...
So there's our electron configuration, okay, and what you're going to see is now there's going to be 3 different peaks, or 3 different intensities that he's going to show us here. So we're going to have 3 different peaks at different intensities, kind of, okay? Scratch that. 2 of the intensities are going to be the same. One of them is going to be different, but the binding energy is going to be different. You'll see.
And if this were nitrogen, remember that's 1s2, 2s2, 2p3, I'd get the following spectrum. A peak down here at 39.6. These are in megajoules per mole.
So we have a peak at 39.6 megajoules per mole. That's the binding energy. That's the amount of energy that it took to get all of those electrons, a mole's worth of electrons, off at that energy level, okay? And then the intensity, of course, is the height of the peak.
And then I'll break the scale here because it's a big jump. I have a peak here at 2.45, and then a peak here at 1.4.
Okay, so real quick, notice the peak at 39.6 and the peak at 2.45 is about the same height. It should be stylized. It should be the same height. Okay, now the reason why he'll get into. Notice that the peak at 1.4 is a little bit taller, just a smidge taller. Okay, he's going to get into that.
So what do these correspond to? Well, if it's nitrogen, I'm down here. I get 2 electrons in the 1s, 2 electrons in the 2s, and 3 electrons in the 2p. So this must be deeper in energy now. This must be my 1s electrons. This must be my 2s electrons. And this must be my 2p electrons.
So he'll get into this, but why does this have to be the 1s? Because this took the most amount of energy. Where is the 1s located? The 1s located is located closer to the nucleus than the 2s is. So it has a greater force of attraction because it's closer, Coulomb's law, and since it's closer, it takes more energy to remove those electrons. 2s is a little bit further out, right? So it takes a heck of a lot less energy in this case. 2p, as it turns out, is actually a little bit further away than the 2s. How do we know that? Because it takes less energy to remove them. That's how we know that.
Read it right off the chart. And the other interesting thing is, you notice I'm careful about the magnitude. It turns out this peak height, compared with this peak height, is in the ratio of 3 to 2. Why? Well, I got 3 electrons here. I have 3 chances to knock out that one. And I only have 2 chances to knock out this one. So this simple, it's not simple, it costs you, set up one of these probably costs you 150 grand, right? But, so you don't need a lot of them, fortunately. But the nice thing about it is I can probe the deep electronic structure of any atom I want. In fact, you can probe the electronic structure of molecules in these kind of devices.
All right, so that was the first PES video. That, I think, gives a great introduction to PES and what we're talking about. I'm gonna stop this video here. There's a second video, but I'm gonna take you back to the Zoom, and then I'll be waiting for you to ask questions. Once we get everybody back in there and everybody has their chance to ask those questions, we'll move on to the next video. All right, so I'm gonna stop this one.